Hello and welcome to our latest STEM Spotlight session. This session has been recorded and will be placed in the STEM Spotlight group on Community afterwards, alongside the previous 4 sessions. Today's Spotlight is focusing on strategies to help the most challenging students develop their science capital. And I'd like to introduce today's presenter, Francis Jones. Francis is an experienced teacher and middle leader who has developed practical kits which can be used by students in alternative education settings. This is at home or with LSAs to access key GCSE required practicals. The organisation he's founded is called STEM at Home. We will be, or I will be asking Francis some questions at the end. The session today has coincided with some downtime on STEM Community, which is why it's just myself and Francis. However, there will be an opportunity to ask questions once STEM Community returns, and we are able to set up a discussion in the chat. So without further ado, I'd like to hand over to Francis for the presentation.
Hi, Steve. Thank you so much again for the invitation to present today. So, as Steve was saying, today I'm going to be running a session about how to run science practicals in challenging environments. So, to give a bit of context on myself, I'm an experienced science teacher who did a PGCE in chemistry, and also I was a middle leader in a rather challenging inner city school. So, I completely understand the challenges that many teachers will face, especially in regards to like behavior, punctuality, and stuff like that. So let's carry on with my workshop for today. So let's start off by asking about this. Do you actually need to run science practicals? You see, the thing is, after all the COVID lockdowns, there were actually surprisingly quite big changes within the science education curriculum at GCSE in the UK. And technically, you don't actually need to run science practicals anymore. Now, I know that may be surprising to quite a lot of you because it was kind of very, how to describe it, subvertly changed as part of the specification. But if you go and read like all the curriculum updates, specification updates, ever since we got out of lockdown, technically we don't actually need to run science practicals anymore. However, if you don't need to run science practicals anymore, then why do we need students to even do science practicals in the first place? The main reason is it teaches theoretical and untangible concepts because depends, like it doesn't matter if you teach physics, biology, chemistry, so much of science is stuff that we can't see, things that we can't directly experience. So a lot of it is intangible. We can't see it. And in all honesty, we do still need to run practicals to try and teach these theoretical concepts, like for the chemistry teachers here, titration. Have you ever tried to explain titration to someone without actually demonstrating it yourself? It's really, really hard. And another issue as well is, despite the exam board saying that students will no longer be tested on their practical knowledge, as all of us have seen from last year and the year and time before that as well, practical based questions always still come up every year in GCSE and A level exams. So no matter what, students will still be tested on the practical aspect. And in all honesty, trying to explain a practical to someone who actually hasn't physically done it in person with their own hands is really hard. And another thing as well is that people learn better through play. Like when you see pictures of a really, really nice place or someone's gone on holiday, would you rather look at the pictures of the holiday or would you rather actually go on holiday yourself? Like everyone prefers it when you actually do it yourself. Now, a common question that loads of people do often ask me as well is, my class is naughty. I want to run practicals, but I can't run practicals in my class. They're really naughty. They're really disruptive. I'm afraid they're going to break equipment. I'm afraid they're going to hurt themselves. I'm afraid something bad is going to happen. But the thing is, though, you can always use your imagination to solve this. And this is what I'm going to be working with you today to try and do. Now, the thing is, though, you can still run practicals and teach the basic concepts, but you don't actually have to follow the guidelines 100%. As long as the students still can understand the fundamental concepts of the practical, it would still prepare them for the exams. You don't have to cut out practicals completely. You can just modify them, use your imagination, so the students can still learn the concepts of it. So basically just modifying it to ensure that students still get the same experience of the process, but just minimizing risk. And that's what today's session is going to be about. It's going to be creative ways in which you can modify practicals so students can still get the same concepts, but you have absolutely minimized the risks involved. So what are the long-term benefits to doing this? One, when it comes to exam season, you don't have to explain an intangible concept to the student. So I'm pretty sure many of us have, like, it's exam season right now. You're trying to explain the concept, I don't know, so like titration, tissue culture, refraction. And then, there's a student that's missed the practical and they're like, sir, I don't understand it. And you try and explain to them and you get that little, like, blank stare. Doing practicals, getting the students to do the hands-on stuff with us, basically kind of prevents this from happening. And most importantly, it also develops their scientific literacy. And also, most importantly for the exams, especially when it comes to 4 to 6 mock questions, it will develop their critical thinking, which is not just something they need to use for exam purposes, but it's also stuff that, students need to learn how to do in their ordinary daily lives. So, Steve mentioned this earlier, but let's try and explain what it is I actually do. So what happened was I ended up leaving the teaching profession to form a company called STEM at Home. So I got inspired by this after I started doing my MA in STEM education at King's College London. And essentially it was a way for me to redesign science practicals to make them fully accessible outside of the ordinary science classroom. So all my practicals are just the required practicals. They've been redesigned, so the same concepts are being taught, but safety has been maximized throughout. And all you need is a basic adult supervision and no subject specialist is needed. So basically, rather than like, a science teacher and a technician having to help one student do a catch-up practical on their lunch break or after school, the students like LSA, Learning Support Assistant, can help them with this one-on-one during their allocated time. So it prevents excessive workloads for the science teachers and technicians involved. So over here, you see on the screen right now are the 28 required practicals for AQA GCSE, the 10 required practicals for biology, the 10 for physics, and the 8 for chemistry. So some of you may be thinking, this is not really relevant to me. I don't do AQA. I do OCR. I do Edexcel. The thing is, the required practical list between all 3 exam boards is nearly completely identical. And a lot of the fundamental concepts are basically the same. So yeah, you'll be able to modify this towards your personal needs and preferences. So let's go through a few examples together. So one of the first ones I would like to talk about is the concept of chemistry, of the required chemistry practical about neutralization, which is also generally titration, really. Now, we all remember titration. You have those big, massive glass burettes, you fill it with acid, you try and see how much acid needs to be added to an alkali, you gently swirl until it becomes neutral. But I know so many science teachers that would not run titration practicals because yeah, they don't trust their class with acid, they don't trust their class with their giant glass burettes. And the thing is, though, it's still a practical that gets questioned quite a lot in the exams. However, there are some modifications you can make to essentially still teach the concept of neutralization, like how much acid you need to add to an alkali for it to become neutral. But you don't need a giant glass burette, you don't need hydrochloric acid. So let's go through the examples together. So one thing I've noticed as well is rather than using like hydrochloric acid, you can just use over-the-counter citric acid. And yeah, they sell concentrated citric acid in the form of lemon juice in your local Tesco's, Sainsbury's, Waitrose, Asda. That works surprisingly well. Like, you wouldn't think like I can use citric acid or lemon juice from Tesco's instead of hydrochloric acid for the titration practical. it surprisingly works. Just make sure it's concentrated enough. Now, rather than using an alkali, you could just use dissolved baking soda. I mean, I think we've all had things before in our classrooms where you have a naughty student, they're holding acid, and you're like constantly keeping your eye on them because the student is holding acid. This is scary. If a student's holding like, you know, lemon juice, you're like, oh, okay, that's pretty safe, really, as well. Like, it's just lemon juice. A few risks, but honestly, they're minimal. Same with using dissolved baking soda for the alkali. And then rather than using a burette, you just get them to use like little 10mm pipettes. I mean, the thing about this as well is you won't be able to get exact quantitative data, but you will be able to get rough quantitative data. And in all honesty, you're still allowing the student to do a modification of the titration practical, but you're just removing a lot of the finer details. And in all honesty, that is just the basics you need to teach. Like, X amount of acid goes to Y amount of alkali, and boom, it gets neutralized. And then also just normal small strips of like litmus paper works really well when it comes to trying to see like how it all gets neutralized. So this is like an example of how you can turn a complicated practical that has loads of risks, and then by just really modifying it quite a lot, you can still teach the fundamental concepts, but you know, much more safer because citric acid, like lemon juice, dissolved baking soda, pipettes, a small beaker, litmus paper. It's really hard for a student to injure themselves on it. So let's think of another one, chromatography. Now, we all know about how hard it is to run chromatography at time. You need like those little blast tubes. You need like the little amino acid stuff and stuff like that as well. You need to use solvent. But in honesty, there are easier ways of doing it. Like, instead of using like, you know, a concentrated solvent, water surprisingly works well. But if you want slightly better results, diluted rubbing alcohol also works really well as the solvent. And, you know, if you don't want to use those little glass dipper things, you can just use felt tip pens, or even like, you know, food dye, just get like a little drop, put it on. It works surprisingly well. And it still lets the student see how the solvent separates the ink. It won't be as detailed as proper chromatography with like, you know, the TLC plates, but it still teaches the concept, and that can be also then used for revision purposes later on. Plus also, it's really hard for students to injure themselves with water, plastic beaker, and a felt tip pen. I'd also really recommend as well is try and see if you can also order a bunch of heat resistant plastic beakers, because those are really, really useful. They don't break when they're dropped. They don't melt, and honestly, they're really, really durable. So another thing as well is the concept of water purification. Now, as we all remember, when it comes to water purification, you just need lots of stuff. You need the tripod, you need the Bunsen burner, you need the heat-proof mat, you need the wire gauze, you need the evaporating basin, all just so you can evaporate some water in the evaporating basin. But what we started doing at STEM at home was using a lot of 3D printing, and we turned that entire practical setup into this. It's basically just like a small little like fork-like thing that holds a tea-light candle underneath, and then, you know, the evaporating basin goes on the top, and it heats it up enough that the solid crystals are generally left at the end. So this depends if your school has 3D printers, but generally, if you buy like, if your school has a 3D printer, generally I just use PETG for this, which is about £15 per spool. It takes about 2 hours to print a single one. You can print them up overnight. And if you pay about £15 for a 1 kilo spool of PETG 3D printed filament, each one of these little devices that you use to like hold up the evaporating bases costs like 15p each to produce, and they're really, really durable. Yeah, so just holds a tea light candle underneath the evaporating basins, and yeah, just evaporates it. Now, another thing that I notice is quite common, especially with biology teachers, is the reluctance to let their students use expensive light microscopes. Now, I can understand like you have all of these light microscopes that cost you like maybe £200 each, and you kind of don't want them to drop it or break it or anything. But here's the funny thing. You can just get these cheap white label like microscopes that cost like £5 each if you buy them in bulk. Funny thing about this, so I learned about this through working in like the edtech industry, but they work surprisingly quite well. Like you think like a cheap little £5 microscope like this wouldn't actually work, but surprisingly, especially when it comes to animal and plant cells, like you can still clearly see the whole cell structure, and students can still draw it and label it. Plus also these run on batteries. They're really quite cheap, so they break, they're easy to replace, but they're also surprisingly really durable. Now here's the fun thing about this. You might be thinking, oh, these sort of microscopes might be hard to get. I can just go to the toy shop and buy them. But the funny thing as well is all toy companies, they basically use the exact same microscope. Like National Geographic's like microscopes, they pretty much just use these ones and just put their branding over it. Gold/GAT. The ones who do like horrible science stuff, they basically use the exact same thing. The Science Museum ones, they use the exact same microscope, so they just change the colors, add some labels onto it. But yeah, look online, try and find some of these cheaper £5 to £7 microscopes. They work surprisingly really well and work pretty much exactly what you need for GCSE biology. Okay, so let's talk about another one. Food tests, so like tests for like starch, proteins, reducing sugars. So the funny thing about this is you really kind of had to carefully read in detail all of the health and safety information because, iodine, Benedict's reagent, burette reagents. But the funny thing about it as well is that when they're diluted in distilled water, Benedict's and burette solutions, they still surprisingly work even when they have been diluted. And essentially, like if you look on Pleeps, the diluted versions aren't actually considered hazardous. So they're no longer considered hazardous. They still kind of work well for food test reagents and like the spotting tiles. So yeah, I recommend giving that a try as well. Try and find what's a good like concentration that still gives you adequate results, but it's also not considered hazardous as well. Another thing as well is the thermal insulation practical for physics. So you can basically just solve that by having like a mug with felt wrapped around it, held in place with a rubber band, maybe even use a polystyrene cup. And yeah, there's also reflection. You might not trust your students with like laser pointers, but every one of them is going to have a smartphone with them. All smartphones have torch functions as well. Just get them to use that. Just get them to see, like, if you change the angle, how the reflected light changes as well. Like, it won't be as precise as a laser pointer, but it still gets the basics across. Plus, also, prevents your students raving around like a laser pointer. And yeah, lets them see how moving a mirror or shiny surface can cause reflected light to move around. You can then just use some creativity to try and see if you can try and teach you about refraction as well. So, those are just some examples that I wanted to give you lot about ways you can redesign science practicals to make them suitable for when a class is challenging. But when you try and redesign a practical for a challenging class, these are the points you really need to think about. One, will they hurt themselves this way? So let's think of an example going back to the water purification practical. There are multiple ways the students can hurt themselves. The gas taps, the Bunsen burners, the wire gowels in certain schools, because I know some old wire gowels still contain asbestos, how hot the whole thing gets as well. Lots of things you need to keep an eye on. With that little 3D printed design thing I did, I can always send you guys the file later if you want to print it as well. All you really need to look about is just the tea light candle itself. Or yeah, just stuff like that. Another thing as well is like, can they hurt others? This is why I really like cheaper plastic beakers. because a student drops it, it's not going to break, it's not really going to cause much damage, and yeah, they don't really hurt. Like, they can't really hurt themselves with a plastic beaker. Another thing is, so if they break it, will the broken pieces potentially cause injuries? Another reason why I'm a pretty strong advocate for plastic beakers. And then also, if it breaks, will it be a financial loss for your department? So it's kind of just like, if a student breaks a £200 microscope that your department's had for like 10 years, yeah, that's not going to look good. Like, they break a £5 microscope like this, like, sure, that's annoying, but not really going to be much of a big loss for your department. So what was originally going to happen before the whole, community thing didn't work was I was going to get everybody to go into like breakout rooms and all start thinking of a practical that you absolutely hated to run and start working together to try and think of creative ways in which you could redesign that practical and think like, what would a student be tested on in their exams? What kind of stuff do they need to learn for this? And what are some creative ways I can get the student to learn this required skill? So I'll just leave it up here for like a few seconds, and then we'll just move on to the next section. Cool. And yeah, if any of you want to know more, get any 3D printed files, or just like bounce some ideas, like my contact information is up on the screen. So you have my business email, that's when I'm more likely to respond to. And I'm really active on LinkedIn as well. Not so much on Instagram and Facebook, so you'll be more likely to get a response from me on LinkedIn. But yeah, that concludes my session for today. Shame we couldn't have like the breakout rooms where we can like, throw ideas with each other. But yeah, I'm going to throw it to Steve for the questions.
Thank you very much for that, Francis. I certainly learnt a lot from there. For a start, the word titration is now in my vocabulary, and it was not 20 odd minutes ago. That was a new one on me. So just talking about, yeah, we're obviously planning on going on to some breakout rooms, but I just want to ask you, what practical did you dislike or have some trepidation about holding?
You are just unlocking like a core memory within me, Steve. Yeah, the one I absolutely always hated to run was the neutralization titration practicals, because glass burettes, man, they are incredibly fragile. I think I've got one over here. Let me just show you what a cheaper glass burette is like. It's like a long glass tube, but these things are so fragile. Like, the student needs to hold them up. They hit to put the clamps there, and it's like one little thing falls down, breaks, snaps, and your technicians didn't have a go because the calibrated really good ones cost like £100 a piece. And then you need to try and get the student to put the acid in the top, but then you also just know that a student might do something silly like, okay, the burette's up here, I need to put acid in the top part, I'm going to grab this whole bottle and pour it in, and you're like, no, stop. And there were so many pieces involved, like, they can involve a student hurting themselves or doing something silly. So for me, the titration practical was the one that filled me up with a constant anxiety, because it was always more of a game of, please don't do that. Stop. No, stop. Okay, do this. Okay, you clearly were not listening. So it was the hardest practical to make sure everything ran safely and no one got hurt. So that's why I really recommend the process that you see on the screen, because if your class is really good, yeah, you can just do the full titration. But if you know that some things are really going to go wrong, or you really don't have space to do titration, yeah, this method that you see on the screen works surprisingly well.
I think that's given me, obviously I've never been a teacher, I'm not from a teaching background. I think it's given me a real appreciation of the anxieties and trepidation that you must have, because I mean, with something like that is so fragile. I'm thinking back to my school days now. Even just a clumsy child could easily cause a problem, let alone a slightly more mischievous one.
Yeah, I mean, I also kind of learned as well that being a teacher is a lot like being a conductor in an orchestra. You're basically trying to conduct like 30 odd people all at once, but rather than one person playing a note out of tune, you have a person spilling acid instead.
Yeah, absolutely. I can see the difficulties with that particular practical. Can you give me just from your teaching career, can you give me a case study or an example of a student who's really turned things around?
Could you rephrase that question?
Yeah, so give me an example of a success story around a challenging student, without naming them, of course, and how you worked with them, particularly from a practical point of view, to make a success.
Okay, so I love these sort of stories. So what I actually found out about was loads of students generally always feel that science, they don't belong to science. But really, that's just their way of masking. I find science complicated. I don't understand it. But the thing is, though, when a student feels like they don't belong in a subject, that's when they start lashing out. That's when they act out. That's where they cause disruption. Because to them, they feel, I don't belong here. I don't care what I do. But the very moment you make a student feel engaged, they start really behaving well because they can now understand it. So they feel like they're part of the class. They don't feel like they're an outsider anymore. They feel like, yeah, I'm a part of the class. Therefore, I want to participate in it as well. Like for me, I engaged quite well with my male students because I would often use a lot of like pop culture centered analogies to help the students understand stuff. So, for example, let's say you're trying to teach something physics related, you would make some kind of analogy to a Marvel superhero they like as well. Like, it surprisingly turns out as well that if you start talking about energy efficiency output and you combine it with like Tony Stark's like arc reactor from like Iron Man, they get that straight away. Or if a student is trying to understand respiration in biology, you just connect it to the Hammond breathing technique in part two of JoJo's Bizarre Adventure. And they're like, oh, I get it now. And then it's kind of like just trying to explain it in analogies that you know the student will understand using like pop culture connections as well. So those are the ones that I feel are quite, how to describe it? Yeah, those are the like the stories that I really love, like when they help those sort of students. Plus, also here's like a brief bit of advice for like many like teachers here that will be listening to this. So many teenage boys that may seem like scary or challenging as well. Turns out most of them are anime fans, really. So literally, if you just find some kind of anime they like and make an analogy to it, it's really easy to engage with them. Like I know so many like teachers in like one of my old school who'd be like really scared of like one student. I was like, nah, man, he's cool. He likes My Hero Academia. We just talked about the latest chapters, and you know, then he just treats me really nice as a teacher. So if I try and think of some practicals that I felt perfectly explain, like a good example of that.
It's that context, isn't it, and relatability that's so important.
Oh, absolutely. So I think when we were doing like a reflection practical before, I think we started talking about like part four of JoJo's Bizarre Adventure and like one stand user's ability with light. And the student was like, oh yeah, I totally get that for. But yeah, being able to connect with the student and explain a concept that they will understand, yeah, really helps them. But then again, I mean, like, what, I'm a millennial that's obsessed with like pop culture. I guess that might be something that might be easier for me compared to like other teachers.
No, I totally understand that. And I think being a little bit more phrasing this question in a more positive way, we've heard about the practical that you were trepidatious of. What's your favorite practical? What would be your go-to practical that you think I can really engage the students with this, and this has got a high success rate, and that you enjoyed staging?
Ooh, one thing that I really, really love covering is the biology quantitative food test practical as well. Like I just love like just getting students like, hey, bring in some food and let's see what it can taste like. Oh, this one has quite a lot of reducing sugars. Oh, this one has like quite a lot of starch, but also works really well with like chemistry because especially when it comes to like, the water purification practical, because I love to play a fun game of like, hey kids, you love drinking Coca-Cola, right? Yeah. Who wants to see how much sugar's in your Coke? And like, I'm sure it's not that much. And then you pour it out, it's like, and then like, wow, there's a lot. And I was like, yeah, terrifying, isn't it? Let's try and do this for a whole 2-liter bottle that I know you drank yesterday, and let's see how much sugar's in there. So I don't want to know. So it's like, but it's great to know just like what's exactly in your food and drinks.
Absolutely, absolutely. I think that, yeah, that context is so important. Thank you very much for that, Francis. That was really, really informative and useful. I know that our members will find it really useful as well. So yeah, I'll be adding that to the STEM Spotlight group when community is back up and running, hopefully very soon. And we'll see if we can start a couple of discussion threads in the groups as well when they're back up and running as well, for any questions that I'm sure you would have had today. But yeah, as I say, I'll also post the links to your website as well. But in the meantime, thank you so much for that, Francis. I really appreciate your time this afternoon. And yeah, I'm sure we'll speak to you soon. Thanks very much.
Cool. So everyone, if you have any questions, or like I said, you want the 3D printed files, feel free to reach out. LinkedIn is the easiest way to like reach me, because that seems to be the only social network I'm actually active on. But yeah, everyone, thanks for watching. Feel free to reach out if you need any help, and yeah, see you in our next session.
Right. Thank you. Cheers.
Bye.